Hello everyone, welcome to AI Anytime channel. In this video, we are going to create our own vector store from scratch. That you would have seen it from the video title as well. We are not going to basically create a vector store like Faz, Chroma, etc. because this is currently out of reach. For this video, that's not the scope. The scope of this video is to understand that how we can create our own vector store, a very small vector store from scratch, to understand that how these things work in backend. So most of the time these are very high level abstract classes. If you are using these libraries like Face, Chroma through some orchestration frameworks like LangChain, Haystack or llama-index, most of the time you will not understand that's what's really happening inside the hood. And that's the agenda of this video. We'll start from scratch. We'll understand what a vector is and what are the different type of vectors that we have to worry about, or we have to understand. And then we'll go on and see how we can create our own vector store from scratch. We'll understand about little bit on the steps, the data structure, the storage strategies, how to serialize or persist, all of those different things we'll try to understand. So this video is mainly targeted towards beginner. So if you are a beginner, you should watch this video. A few of the things I will also explain for intermediary and experts like some of you who already have great experience with vector databases. So let's get started. You can see that I have my tab on today, and we are calling it vector stores. So if you don't know what vector is, in our basically the school times, right, when we were studying physics, we used to get this question of 2 marks. Okay, I used to get it of 2 marks question, the difference between a scalar and a vector. So it's a very famous question. So vector is like an object. It's a mathematical object. If you talk from a mathematics standpoint, it's a mathematical object that has both magnitude and direction. And we'll talk about it, that what I mean by it. So it represents some quantities having both the things, magnitude and direction. And when it comes to machine learning or NLP or recommendation system, so vectors are again used to represent some data points that can be your features, that can be your embeddings of objects, etc. That's what a vector is. Now we will keep it more inclined towards natural language processing and machine learning, but it's again part of mathematics. Everything that we are currently doing in generative AI is derived from statistics or some of the mathematical equations. So we'll talk about it wherever required. Now I hope you can see it here on vector store. We have something. So let's take a simple example. So I'm just going to write a simple example here. And so it's an vector is an ordered list when it comes to your natural language processing, ordered list of numbers or even scalars, that can have a list of scalars as well that are arranged in an specific order. So each of this value inside a vector is called a component. So let's now understand like this. We have something called V. That's how you can represent a vector by a V or an X. Now I say, let me see also. So you can see here, okay, I hope so. Now suppose this is, and how do we basically define a vector when it comes to mathematics of, or even let's talk about machine learning and NLP. This is how we define it through a square brackets or an angle bracket. So if you see here, I have a square bracket and I'm writing something like this: 2 -1 3. Now this is a three-dimensional vectors. Why there are three-dimensional vector is because because it also has a three components inside it. All of these are called components. So let me just write it here. These are called components inside a vector. You can see it's a list that I currently having. If you talk more Pythonic terminology, you can see a list having three components. Okay, 2 -1 and 3. Now it's a three-dimensional vector with three components. But when you are really working with like a number of documents, etc., we'll see that list that we'll talk about. I'll show you when I'm writing the code. So once we write the code, once we create a vector store, in memory vector store, we will see all of these steps, step by step. Now Each component represents a magnitude and direction along a specific axis or dimension. If you plot it that way in a 3D vector space, you will see that each component has a specific axis, and let me just write it here. So a specific axis or dimension. So this is a very simple definition of vector. Now there are two different type of vectors that we come across when it comes to natural language processing. One is let's write it over here. So I'll write major types. Now this can again go if you go in more details, there are more, but we'll talk about that we are nowadays facing when it comes to search or semantic search kind of a task that we are looking at. We come across sparse and dense vectors. Okay, so let me just write it over here. I'm just going to call it dense, and the second one is sparse. So these are the two main, let me just, yeah. These are two main types of vectors that we see, the dense and sparse. Now, what do we mean by this, guys? Okay, so I'll just make it a line here to separate and then write something here. Okay, now let me write it. So dense is something, the most common types. Let me just write it also because I will give you this screen grab in description for you to have a note kind of a thing, or if you want to go through it later, you can also go through it. Most common types, and they have non-zero values, okay, in the list, the order list that we can see here, which is v2 minus 1 3. I will explain that. It has mostly not mostly, it has non-zero values. So dense vector is having non-zero values. So if you look at this vector that we have 2 minus 1 3 v that we have, this is basically, let me just make it a little bigger. I have to make it a little long. Yeah. Now v2 minus 1 and 3, it's basically these are the values, and they are all non-zero values. If you see that we have here non-zero values, and all of this that you see hold some kind of information. Okay, so they hold some information, or some amount of information would have been a better terminology to write here, but hold some information. And that's where we look at the try to capture the semantics when we are doing the semantic search, and when we're writing the code. I will explain what I mean by this statements. They hold the information, all of these components inside a vector, and that's where we derive the semantic information from. Okay, now these are your dense vector, which are most common types, having non-zero values and hold some information. These are, again, if you go and read it on like internet, you will find a lot of information, but the video will get longer. So I want to keep it more concise but explanatory, that you can understand. Now these are the dense vector. Now if you come to sparse vectors, what do we mean by sparse vectors? So very, like, it's vice versa, right? If you see non-zero values for dense, then it will be opposite here for sparse. It can have zero values as well. So let me just write a zero component. Zero components or elements to write, if you are looking at a list kind of a thing, elements, and it's used when data has a lot of dimensions, but most of those dimensions are either empty or have negligible values. So these are, again, let me write it. I hope you can see here. Used, let me just go up. Okay, used when the data has a lot of dimensions, when the data has a lot of dimensions, having empty or negligible values. Okay, that's what I'm writing. For example, if you look at, let me just give you an example. These are very common for, let me just write it from green because this might be helpful. Common for word embeddings. If you look at the most used, what are the most used areas when it comes to both types of vectors? Sparse vectors are very common for word embeddings. If you look at the one of the example, like if we have v equals to 2 minus 1 and 3 for dense, you can represent something like this, the numerical values, and then go 0 0 0, and then dot zero, something like this. So sparse can has, zero components or elements. So this is a very high level, definition and example of a vector, the components and the type. These are more Pythonic because I want to also show you that how we can, write code on top of this, because that's what our agenda is. Now, this is about vector. We'll go a little more theoretical before we start writing code, and that is the steps, steps to create vector store from scratch. We are not talking about vector database here because this is beyond this video. The scope is not currently that I can work on in this video. So steps to create vector stores, maybe due to whatever, the infrastructure, the data center, whatever. Okay, we'll focus on steps to create vector stores, and those also in memory vector store, because we do not have, we don't have that. Like, even if you want to scale, we don't have the distributed computing for that scaling, right? We don't have it with us right now. Now, what are the steps to create a vector store? If I list down few of the vector stores that are in memory vector store, I will talk about few which are very famous. For example, FAS, I think it was like Facebook, and then ChromaDB. The two most used in-memory vector stores when it comes to generative AI applications or LLM powered application that we are, that we are currently working on. Now, what are the different ways that, we can basically uh, steps to create a vector store? So before that, let's talk about here some of the applications, that where do we use vector stores. So applications is like we used in machine learning, we used in natural language processing tasks, we also used in recommendation engines. So these are a few areas. So guys, this is going to be little verbose, this is going to be little explanatory. So if you want to just focus on code, you can skip this part of the video and just directly go to the code part, okay, where I'm writing the code for creating our own vector store. But steps are important for you to understand that what are the steps required if you really want to, create your own vector store. Because, in upcoming videos, definitely we are going to create a library of this. We'll put it on PyPy and then see how we can use our own vector store in some capacity, not with the large set of data that we are going to create, but for few of the sentences or one or two pages. Now, if you look at the steps that we are going to talk, the first thing that is required is, so let's call it step maybe A, and the first thing that is required is a programming language. So what programming language we are going to, use or write code to create this vector store? Few commonly languages are, C, C++, Java, and Python. We will use Python because that will be easy for us to develop. That might not be scalable or efficient, but we are going to rely on Python as a programming language in this video. So that's the programming language. Now the next comes is the data structure, which is the most important thing when you want to create a vector store. The better vector stores in the engineers or the software developer, the SDE folks, when they work for this creation of vector databases, they are focusing more toward data structure, because that's what make your vector store or vector database, efficient, right? So let me just write it a data structure. Now for simplicity, we'll keep a simple data structure in this video, but if you see what kind of data structure that we can work with, so it's important for efficiency as well. And we are going to work on in memory. So let's write it's important. So I'm going to write in memory. This is our target. So let's write that also, our target. This is our target data structure, and these are important for efficiency. Important for efficiency. Now this is data structure. The third thing that we need is, so let me call it C, or rather we should have gone with 1, 2, 3. Now we're going with alphabets. Okay, A, B, C, and the C will be, we are done with programming language data structure. The next is storage format. How are we going to store this vector? So let's call it storage. So let me write here what's happened with the pen. Storage format. This is what the third thing that is important. We have to decide on a format for storing the vectors in memory, that too in memory. So why do we need storage format? To storing. So we're going to storing. So storing the vectors. Let me just write storing the vectors in memory. Storing the vectors in memory. And what are the things that we can look at when it comes to storage format? So it can be arrays or list, or then your custom data structure. So we were not going on custom data structure, but if you find some inspiration from this video, you can go ahead and use your own custom data structure. We will probably rely on these two, arrays and list. That's what we are going to use. So we're going to rely on arrays and list. We're going to rely on in memory, and we're going to rely on Python. So this is what we are selecting right now. So Python, in memory, arrays and list as a storage format. The next thing is, let me write D here. The next is loading the vector. So I will just write very high level, loading the vectors. We'll write a method to load the vectors, which is not a big deal, loading the vectors. And the next thing is indexing. Now, indexing is again I'll say the second most after data structure. Your indexing strategy. Indexing. Just think indexing like a table of content. When you get a book, in the book, it helps you search faster, search efficient. Now you have a book having 1,000 pages in that book and have different topics and subtopics. So different topics and subtopics. Indexing helps you, the table of contents in the book, to go at that page number and find it out. So it helps you search faster. So when you want to build a semantic search application, so you should focus on indexing, right? That's what these vector databases like Pinecone, Weaviate, etc., they focus on with different algorithms. I will explain that what kind of algorithms we can use for a better indexing. Okay, so in indexing, let's write here, indexing is important. I'll write, if you want to make a note of it, let me just write it, because I will give you this snapshot in the video description so you can have it for later. So for efficient retrieval of vectors, these are very important. That's why we have to consider. Now, what are the algorithms? Otherwise, I will forget later. So let me also write few of the algorithms that we can work on. So technique is like the first technique. How should we write it? Let's write one here then. Okay. Okay. Excuse me. Okay. Now the first is you are having hash maps. So creating hash maps. Okay. If you are working on an indexing strategies, you can look at this different techniques. If you are working on in memory, even not on in memory. Now we have advanced techniques like, we have data structures. We have data structures like KD trees and ball tree, etc., etc. For speeding up the retrieval process. Now, ball tree and KD trees can be very handy if you want to, etc. For speeding up the retrieval process. So speeding up the retrieval process. I don't know, guys, if I am taking too much time to explain this, but I want to explain it because few of you have, suggested me to create videos for beginners. I assume that you are a complete beginner having no understanding, and if you have some understanding, you should skip this part. But I'll request you, I will urge you to go through the entire video and try to understand that how this step by step it works, how people have created Fast, Chroma, Pinecone, Weaviate, etc., etc. This will help you understand, create that ability to think that how you can create your own. You can start from a small and then you can scale up. Now indexing, and then we go to querying. So querying is like how we query the vector store. So we're gonna implement some methods. So implement, let me just write it over here, implement methods or functions, whatever. Okay, functions to query. The criteria, you would have heard, right? We are going to focus on similarity because we are going to use cosine similarity. You have L1, L2 dot products basically. Then we have L1, L2 Euclidean. Okay, so we have different way of querying this. So similarity, then dot, then Euclidean, then we have Jacquard, then we have Levinstein, blah blah blah, right? Thousands of there. Okay, you can look at what similarity. For similarity, you have Jacquard, Levinstein, cosine, Euclidean. You can look at all those different techniques of querying this, the algorithms. Then you have range. Based on range also you can do it, but we are going to focus on similarity. Let me make it green. Okay, I'm not able to select green, that's why. Okay, now I can. Now a similarity range, and then you can also have your own specific identifier. If you think that, okay, you have special identifiers in your data, okay, that you can also define it and do it. It's all how you write the logic, guys. Very intuitive, isn't it? Now I'm going to write E, and querying is done. After querying is, sometimes you also want to update vectors. Now this is a common question that, hey, I already have persisted a vector store, and now I have a new document. If I create vector and then again up, like, basically store it in vector store, what will happen? Like, will it update or it will overwrite the previously created vector store? So this is also very important to understand. Now update vectors is like a, I'll just write add, modify. We'll explain that when we are writing add, modify, delete operations. That are the operations that you have to do. Now EF, oh, I forgot the numbering, guys. EF, this will be G and then H. Okay. Now next is memory management, which is very important. If you have a bigger file, like a file becomes really big, if you have too many vectors in your store, it might crash you, right? It will give you some memory error. And also we also have to focus on memory management, how we're going to memory, especially we're dealing with the, so I will just ignore it because we are just going to do a small experiment here, but you have to be worried. You have to be worried when you create a bigger vector store or vector database. Now next is serialization and persistence. And you would have heard about this word, guys. Okay, persist directory. When you are using ChromaDB or FAS or whatever, save to disk, load from document, whatever. Okay, save from document, whatever that you have, the functions or method. Now serialization and persistence means we have to persist the vector stores, to the disk, now if you want to save it and load it separately, if you don't want to just do it from cache in your runtime, then you can also persist the directory. That helps you. So you have to implement serialization and deserialization techniques. Okay, so I'll just write it sir and desir. That's how we define in Rust, by the way. This is how we define ACR and serd. Okay, ACRD. So implement serialization and deserialization. Okay, I love Rust, guys. By the way, I'm spending a lot of time to learn a Rust programming language and build. I also have a couple of videos. Now implement ser and deserialization to save and load the vector store. Now couple of more GHIJ. So now again I'll just write a few things. We're also going to do some testing. You should testing optimization. You should test it out thoroughly. You have to test it extensively before dropping it in market as an open source library. HIJ. Then K can be the next can be documentation. So let me just finish it. Documentation and scaling. Now the scaling part will come. So scaling, again, you need distributed computing, and also we need distributed computing and scaling techniques. Now this is what are the steps, guys. So you can see the steps. We have around here 11 to 12 steps, right? We have programming language, so we are going to use Python. We have the data structure, so we are going to rely on in memory, like that is important for efficiency. For storage format, we will look at arrays and list. For loading the vectors, indexing, blah blah blah, querying, similarity range. So this I will give you in the description, the entire thing. Now so far, let me keep it aside, otherwise you will say that uh, I'm only creating this theoretical aspect, not coding. We'll now jump into the coding, guys, and we are doing it raw. We'll do it live. We are not doing it like edits and all. It's all live. Okay. Now, so this is done. Now, what I'm gonna do here is my favorite part, the code. So let me charge in. Let me minimize this. And now what I'm going to do is I'm going to create a folder here, and let's call it VS something, like let's call it better in vector store project. This is what I'm going to create, and inside this, now I'll make it my mic little here, vector store project, and here we're going to write all our code on my monitor. Let me set up my monitor quickly. So what you have to do is we are going to do it from scratch using NumPy, okay, in pure Python. So what I'm going to do is I'm going to create a virtual environment very quickly. venv.venv. It will create me a virtual environment. If you already have a virtual environment, if you're using Anaconda stuff, you don't have to worry about this. Now cd.venv scripts dot slash activate and couple of cd dot clean VS Code. Now I will open this in VS Code, and then we'll start writing some code logic here. Now it opens here. You can see in VS Code I am using sets of purple as a theme. Some of you asked that which theme I am using in VS Code. If you have any recommendation, please write it down in the comment box. Now here I'm going to create a requirements txt first. So let's just do it. Requirements txt, and I will write numpy. So let me just do a numpy thingy here, and I will just do here pip install. Let's install this pip install -r requirements txt. It will install numpy for me. Now what I'm going to do is I'm going to create a separate Python file which will have our vector store class. So I'm trying to make it more modular. So I'll keep on adding more features, method, functions in upcoming videos, and we'll make it a full project like a library in coming videos. So what I'm going to do here is I'm going to call it as a vector underscore store dot py. So in this we are going to start very basics, that how can it look like, okay, and those things. Now you can look at that my numpy has been installed successfully, and now what I'm going to do is I'm going to say import numpy as np. This is what I'm going to do here. Now we will define a class. You can see that I'm using Copilot, GitHub Copilot, which seems that very intelligent, and it show you a class. So I'm gonna use this class, but I'm just going to write it more like this case. We have snake case and camel case. So for Python, for JS, people follow differently. Now in vector store, this is my class. Now class vector stores, the first thing that we're going to do, we'll have 4 or 5 functions in this video. So let's first have an init function. In Python, we have init function. You can see it says init, and I'm not going to worry about this dimensions and all for now. But this is a good recommendation, guys, by Copilot. So most of the vector store, you can also define your own dimensions, like 768 that Pinecone suggests for most of the LLMs like Vertex AI, Text Bison, or whatever, right? So you can also define those. But I'm not interested in that right now. Let me just remove all this thingy from here. I also remove dimensions. I will only keep self for now. Now here in self, what we're going to do is we are going to have a vector, like a dictionary to store vectors. So let's do it. So what I'm going to do is self dot vector underscore data, self dot vector underscore data, and this is going to be a dictionary. So let me also comment it, a dictionary of to store vectors. So a dictionary to store vectors. As you can see, it's also suggesting me that, okay, you also use this, but I'm not going to use it. We'll have an indexing structure for retrieval also. That again going to be a dictionary. So for now, let's define self dot vector index. So I'm going to have a vector index, and I'm just going to again have, you can see it. Okay, fine. A dictionary to store index of vector. Indexing structure will be a right word. Okay, dictionary. A dictionary to a dictionary for indexing structure for retrieval. Okay, now this function we are okay, guys. Now what I'm going to do next is I'm going to have a function for adding the vector. Okay, so let's do it. So what I'm going to do, I'll just make it little down. I'm not able to see my monitor. Now define add vector. Now in this function, we'll have vector ID and their vector, like that is right, but I will have my own naming convention. So define add vector first we again self is fine, and then I'm going to have a vector ID. So let's do vector ID, and then I'm going to have the vector. This is right. It was right, but anyway. Okay, now let's write here, guys. We should write okay, now here we have to we can comment it, add a vector to the store, then this is not required. Add a vector to the vector store. I also want to comment it down because later I can also reference it. Add a vector to the vector store. You will have arguments like vector ID, which is a string of. So let's do it. Self dot vector data, and that will have vector ID, and then it will have vector. Then it will not this. So once we have the vector data, we also need one more function because we want to update the index. So we will write that function later. So let me just use a function here. So update underscore index, and here I'm going to pass my vector ID and vector. So we have to write this function below. So we'll write this function. Now add a vector to the vector store. This is done. Let's also define the arguments here, guys, for your, if you're doing it from scratch, let's do it from scratch. Now arguments. So what are the arguments? You can see it, a vector ID. Let me also define the type of the data. That can be string or int as well. Okay, the vector ID, and unique identifier for the vector, and then vector, the vector to be stored. Okay, so this is going to be a numpy. It's going to be a numpy.nd array. Okay, this is what we're gonna write. Now this is your type of the data, the vector to be stored. Okay, so let's write it. Let's treat it as a data, the vector data to be stored. Now this is how we're gonna write it. Let me just remove this thingy not required. Now we are done with this add vector, guys. So this function is okay. Now we're gonna write a get vector thingy. So define get vector method here. So define get vector, and that will have only your vector ID. Okay, so what I'm gonna do is, okay, so I think this is right. Okay, so self and vector ID, and then I just get a vector from the vector store. Okay, this is correct. Or get retrieve vectors would be the right method, but let's define get vector. Vector ID, a unique ID for the vector, and then returns the vector data if found, or none if not found. Okay, the vector data if found, or if found, or none if not found. So if there is nothing, then it will just return none. So return self dot vector data, self dot vector data, self dot vector data. But this is, we also need, let's use vector data dot get. This is right now, because then we say none. Let's remove by default, it will be that vector ID. Now this looks good. Yeah, so we have two methods that we have written, add vector and get vector, into our vector store class. Now what I'm going to do next is have one more method for updating the index. So let's call it update, and this is going to be our update index. Okay, and let's follow the right update index, and here what I'm going to do is define update index, self vector ID vector. This is right, and it says vector ID string, a vector ID for the vector, and vector ID for the vector, and unique ID. So this is right. Let me see the identifier of the vector. This looks nice. So in update index, what I'm going to do is, in update index, we will say for existing ID, let's have a variable existing ID. So for existing ID and existing vector. Okay, so if there is already an existing ID and existing vector, in self dot vector underscore data dot items, which is a right suggestion. Now here we'll do a similarity. So let's have similarity. Now what we are doing here, guys, if there is already an existing vector like this in the vector store, the vector data items that we have. Now we are going to calculate the similarity. So in similarity, I'm going to have dot. Let's have a dot. So np dot dot from numpy we are using it. We're not using any library. Now np dot dot vector existing vector, and then we define it by yes linear algebra dot norm vector. I have to check the formula by the way. Just give me a minute. Uh, Linear dot norm vector and existing vector. I think this is right. So let's go ahead with Copilot suggestion. This looks nice. Now, once we have count the similarity for the existing with the new one, now what I'm going to do is I'm going to say, okay, if existing ID is not in cell vector index, this is right, then cell vector index, existing ID, and then you have a new. This is fantastic, right? So understand this is how very basics, but the fundamentals will be same, if you are working. So I'll just come out of this if now and self dot vector index existing ID vector ID similarity. Fantastic. Now we are done with this update index as well, guys. Now define update index is done. Get vector, self vector ID, add vector. So we have three methods that we have written so far. Now what I'm going to do next is I'm again going to define a find similar vector. Now we have written the steps for indexing and adding vectors, updating vectors. Now what I'm going to do next is write the function for get the similar vectors for querying. So let's do it. So I'm going to say find underscore similar underscore vectors. This is what my function is. So self, and then I'm going to have query and underscore vector, and then query underscore vector, and then num underscore results. This is what I'm going to do. So let's have 5 result as default. Okay, here is an input parameter argument. Now num results as 5. Now let's have some. I think this is right. So find similar. Let me read it. Find similar vectors to the query vector. This is right. Query vector, which is numpy d array, which is int, and list a list of tuples of the form vector id to vector id, and let's call it similarity score. Then it matches what I have done. So results, which right now for vector id, vector in self vector data dot items. This is right. Now similarity, we're looking at np dot dot query vector vector np. This is right. Results dot append vector id similarity, and then we are sorting it. Let me just also define it here for you for better understanding. So sort the similarity in descending order. Now this sorts it and then return the top end result. So let me just do return the top end results. Return results and then num result. Excuse me, sorry. Now we are done with our small vector store class, guys. In a class having few methods like adding vectors in memory vector store, get vector, update index, and find similar vectors. So what you can also do, you can also write some logic to persist in a directory. That will help you save in the disk. You can define some file path and all, and you can also do it. So that's maybe the exercise for you. Now what I'm going to do next here is, guys, I'm going to create an app.py file. So let's do it, app.py, and we'll test it out with some logic. So what I'm going to do, I'm going to say from vector store, okay, not caps. Okay, it was caps, by the way. I'll make it, this is not the right way of naming. Okay, so let me just vector store. Now what I'm going to do here is I'm going to write vector store import the vector store class, and I also need numpy here. So import numpy as np. Now here I'm not going to explain about some of the techniques like tokenization, vectorization, because we are going to try it out our class. But anyway, I can also explain it. Let's initiate the class. So vector store equals vector store. Now we have create a, let's also write it comment so you can understand it better. Create a vector store instance. Now this has been done. Let's define our sentences. Now suppose if this is coming from your document, okay, now I'll write it. You are using LangChain, directory loader, or whatever to load these files, right? and define your sentences. I will define a list of sentences. So let me just do a sentences here, and in sentences I'm going to write a few sentences. The first thing, let's write about something like fruits. Fruit, let's write I eat mango. So this is what I'm writing, I eat mango. Or let's keep it first the lowercase. I eat mango, this is first. Now mango is my favorite fruit. This is right. Mango is not my favorite fruit, by the way. I just know I am. Mango, apple, and oranges. Oranges are fruits. Now, this is done. So, fruits are good for health. Now, suppose this is your text that you have your PDF documents, you are extracting it. Here we only have five. You will have 5,000 or 5 millions, depending on the how big the file that you have. Now, what I'm going to do is I'm going to tokenize and create a vocabulary. So we are also going to create the vectors here. Let's see how we can create vectors. Now, what I'm going to do here, let's write tokenization and with pure numpy, with no NLTK, no scikit-learn, nothing. Okay, so tokenization and vocabulary. I don't know what's the spelling of vocabulary building. Okay, let's write it like that. I don't know if that's right. Trust the GitHub Copilot. Now, tokenization and vocabulary building. So let's have a vocabulary, and I'm gonna use set here. So set method, and if you read it, I don't know. Okay, vocabulary equals set, and I'm going to say for sentence in sentences. So this is right. I'm going to create tokens. So tokens equals sentences anywhere they are lower cases, but you should always do lower dot split. This is right. This is my token is, and I'm going to update the vocabulary, the set that you see. You can also do a list and you can update it, right? That's what we're showing, or a dictionary. Now vocabulary dot update, it creates a vocab for all the unique tokens. That's what vocab does, by the way, guys, if you are not aware. Okay, in natural language processing. Now I'm going to assign unique indices. That's what we're going to help in the index as well. So we're going to define indices, unique indices, to words in the vocabulary that we have. So let's do it. Assign unique indices to words in the vocab. Okay, that's what I'm going to do. So I'm going to say, okay, word to index, which was right, by the way. GitHub Copilot was saying word to IDX, which was more better. Okay, so just this is right. So word I for I, word in enumerate and vocabulary. Very basic Python, not needed to explain. Now we have assigned our unique indices here, guys. Now what I'm going to do is I'm going to do vectorization. Okay, so vectorization is step. So let's do it. Vectorization. Now you can see vectorization. So we will do the vectorization. So for sentence in sentences, let me see. For sentence in sentences, we're gonna have let's remove this. Looks complicated. For sentence in sentences, I'm gonna have tokens, and my tokens are nothing but lower or split. Again, the split for vectorization, the same that we used. And now I will have a vector, and that vector is going to be np dot. This is right. Length of vocabulary and numpy dot zeros. So what I'm going to do next is for tokens in tokens. This is right. Word to index. Now you can, for vectorization, you can also use this libraries that we have, in scikit-learn and some other libraries that NLTK to vectorize it. But here we are doing with the plain Python NumPy. Now for token in tokens, vector word to index token equals plus. Yeah, this is right. Now what I'm going to do next is just do sentence vector. Sentence vectors. Let's have a sentence vectors of sentence, and this is right, vector. Now we have to store this. Now we have the vectors. We got our vectors for the above sentences. So what we did so far, we initiated a vector store class, then we defined some sentences, then we set a vocabulary, and tokenization and vocabulary building that you saw in the line 15 to line 20, and then we assigned unique indices to all of the unique words in that vocab. Okay, and now what I'm doing next is creating vectors. Now once I have the vectors, I will store this in the vector store. I'm going to add it. So let's do it. So that's what I'm going to do. Add vector to vector store. This is what we are going to do. So I'm going to say for sentence vectors items, for in sentence vectors dot item, this is right, vector store dot add vector, and this is coming from here. Now we are utilizing this add vector function that we have written here in app.py. You can see now this is what we are doing. We are adding our vector here. Now this is done. We have added our vector. Now we're going to search for the similarity, right? So searching for the similarity. Okay, now this is what I'm going to do here. I'm just going to have a query sentence. Let's define a query sentence that we're going to search. So query sentence, and I'm going to just search like what we don't have. Let's write mango is the best fruit. Now, if this is your query sentence, this is what your prompt is, by the way. Okay, if you think like that, okay, not exactly the prompt, but if you want to do a semantic search, now this is your query sentence. Mango is the best fruit. Now, your query vector will be, what will be your query vector, guys? So query vector will be your np.zeros and length vocabulary. That's how we are creating vectors. Now we have a query tokens to make it again that we have done so far, the lower and split. That's fantastic. Now query sentence, what I'm going to do is for token in query tokens, this is right, all the token in this query tokens, you do query vector to query vector word to index. We are using this word to index thingy here that we have, and then token, I think this is right, word to token. Okay, this is fantastic. Now what I'm going to do next is we'll have a similar sentences, and in this similar test sentences we're going to have vector store dot find similar vector class that we are using from the class that we have, vector store class, the method find the similar vectors. And then let's only have two numbers. So the default was 5, so it might give you error because there are no five actual sentences that we have in our list. We don't have. Now number results equals to 2, and I'm just going to print that. So what I'm going to do here is let's print it in a little more verbose so you can understand completely. Now I'm going to say print, and my query sentence is my query sentence. This is what I have asked for, and now we'll have a similar sentences. And for sentence similarity, I think this is right, print sentence similarity. I can also, let's print the score also. So you should also look at the score. So for sentence similarity in similar sentences, I'm gonna say print and then have formatting and sentence to okay, this is right, if, and let's sentence, I will just remove this sentence. Now this is right, and I'm gonna here say similarity, and then this will be similarity and to having some floating points like, and this is what it is. Now this is right. So let me explain what we did here in this, guys. So now you can also build an application, you can extend it further, but I will quickly explain because we are done with our codes for this video. Now if you look at this vector store, what we did, we created a class called vector store here, and where we have an init function where we creating two very small dictionaries for storing vector and one for indexing structure for retrieval. And then I have a function called add vector. In add vector, what I am doing, I have this function. What it does, it looks at the vector ID and the vector, and it uses the update index that we have defined in below. If you look at the update index here, it looks at the existing ID and the existing vector in the already created vector items, and then it calculates through dot product, and then it gets the similarity and then update it if there is any need, okay, in that. And then what it does, it also gets, we have a function called get vector that helps you retrieve the vector, and through this similarity vectors function that we have written. That's what we have done here, guys. Not the best, not at all even optimized by any means, but this is what you can start. Now here we have initiated the vector store instance, defined our sentences, the sentences in which we want to create the vectors, and later search within this vector space. Now we have these sentences, and then we set this tokenization and vocabulary building, create a vocab, and this is what we are doing here, updating with all the tokens, then assigning unique indices to word, then vectorizing it, adding it, and then searching it, and then printing. That's what we are doing here, guys, in this video. Now let's run it and see if this works. So now to run this, we're gonna just open our terminal, and we're already inside the virtual environment. Let's just do python app.py. When I'm going to hit enter, I'm expecting that it will give me two results, which are similar to the query that I'm asking or searching for. Now when I just do python app.py, now you can look at the query sentence. Mango is the best fruit. Similar sentences are, mango is my favorite fruit. Similarity, and I eat mango. So we got two similarity scores for two responses that we got. So you can look at this. Mango is my favorite fruit, which got around 77% similar to what we have searched for or asked for, the query that we did. Mango is the best fruit. And you can look at mango is fruit. That's we are good looking at. Now, this is how it works, guys. If you look at, let me just do one thing. Let me just go back to vectorstore.py. This is a very basic example that we worked with, very basic logics. Now you have to add many other features and optimization of with different algorithms. That's what I am gonna do, of course. That's why I've created a modular class here that I can work with. But I hope you got an idea that how you can get started from scratch with different steps that I've told you, that how you can create your own vector store, in-memory vector store with these techniques, and you can understand that how it works. So in this file, you would have seen all the logics for the vector store. The code will be available on my GitHub repository. You can go ahead and fork it from there, and you can start working on this, extend it further. Let me know if you have any open source project in mind that you are currently working on. If you want to collaborate, if that excites me, I'll be more than happy to work with you on that, okay, on these kind of things. Any orchestration framework, any vector stores, mainly something related to graph, probably knowledge graphs, etc. We can do that. Now, in this, what we did, we initiated a vector store class, have some sentences, tokenized it, assigned some unique indices, some vectorizations, and then search for the similarity. And you got the response over here for that particular sentence that we have made, that you see here. Excuse me, here mango is the best fruit. You can also build a web app to and to build it. Now, because here we have a small vocabulary, you will have a big vocabulary depending on what kind of data that you are working with. So I hope you learned something in this video, guys. I just wanted to create a basic beginner video where the beginners can understand the vector, the type of vectors, how to create their own vector stores, and what are the underlying magic that happens, within a vector store that you see with Fast, Chroma, Wavy8, Pinecone, etc., etc. Some of them are vector database. If you have any thoughts, comment, feedback, please let me know. Comment in the comment box below of the video, and you can also reach out to me through my social media channels. Please find those in the YouTube banner link and the channel about us. That's all for this video, guys. See you in the next one.